Hey guys, hope you're doing well. Let's get a look at what we're doing. Bear with me just a moment. I'll go ahead and share my screen so that you guys can see what's going on. And again, we're going to start talking about some new material here. This is stuff for test 2, so I wouldn't worry about it so much at the moment. I've pushed back the due dates for this until after the first test. So we should be okay with that. Now, my goal here is to get this recorded, get this up for you guys, then get that test finalized, and then start the rest of the recordings. I think that we've finally gotten to a place where the technical difficulties are sorted out. And so hopefully we'll be able to do that. So let's see what we're going to talk about today. We're going to be talking about common ion effect. And that's going to be from chapter 16, section 2, the common ion effect, section 8, common ion effect and solubility, section 9, pH and solubility, section 10, complex ion equilibria and solubility. And then we'll talk about an application of the solubility product where we look at qualitative analysis and how we can manage to do that. And we'll talk about how that works. So the common ion effect. Well, okay. Let's talk about CaF2, which is a slightly soluble salt. It's not a great thing to be able to dissolve. We see that in pure water, it has a solubility of just over 10 to the minus 4th, okay? So it's not a greatly soluble salt. But if I add NaF to this, which then gives us more F minus in solution, that solubility goes down fairly rapidly. And that's because that F minus being from 2 sources means that we have an effect on that equilibrium. We aren't able to dissolve as much because there's already F minus present. Okay, let's take a look at how that actually looks in terms of our ice tables. So the next thing we're going to look at, this first ice table represents CaF2 with just pure water. So we're looking at CaF2 with a KSP of 3.9 times 10 to the minus 11th at 25 degrees. We want to calculate the solubility of Ca2 plus, given this KSP expression, and given our conditions that we're looking at. Now, I'm going to go ahead and share with you my fancy piece of paper so that you can see what I'm writing down when I go to solve this. Now, what you're looking at here with this table that I've put in here, this is how I've manipulated information in Excel. So that's what I use to calculate all of this stuff. And I set these up so that they're pretty and they look nice and they can go on the slide for you. But it doesn't necessarily tell you everything you need to know. And so I want to see if we can get that in a better place. So I'm going to set this up on my piece of paper and I'm going to show you how I pull information out of that question to try and set up my ice table and then to solve that problem. So it says that it's CaF2. And that I have a KSP equal to 3.9 times 10 to the negative 11th at 25 degrees. Okay, I want to know the solubility of Ca2 plus. So I know that my KSP for this is going to be equal to Ca2 plus times F minus squared. And of course, I know that because I know that if I do CaF2 solid to become Ca2 plus aqueous plus 2F minus aqueous, sorry, I can set up an ice table for that or a rice table, depending on how you want to refer to it. And again, since this is solid, I don't care about that at all. It's not going to appear in my ice table. Now, do I include it to show the entire reaction? Of course I do, because I'm anal and that's what I do. But we're only concerned about the Ca2 plus and the F minus, which initially are 0. Okay. I know that for every CaF2 that I break down, I get 1 Ca2 plus and 2 F minus. And that's based on the stoichiometry of this equation. So since I get 2 F's out of this, right here, I have to make that sure that that's a 2x down here. That stoichiometry is how we get that factor. Okay, that's our change. And then we want to talk about that equilibrium. Well, I know that to get my equilibrium values, I have to set my KSP value, 3.9 times 10 to the minus 11th equal to that Ca2 plus, which is x, times the F2 minus squared. So I have a 2x for the F2 minus, and that has to be squared. So that's the expression that I need to look at. So I'm going to flip this just because it makes my head happier to do that. So when I multiply, when I square the 2x, that gives me 4x squared. 4x squared times x gives me 4x cubed. And that's equal to 3.9 times 10 to the minus 11th. Okay. Now, in order to solve this, I'm going to have to divide both sides by 4. And that's going to leave me with an x cubed equal to whatever that calculation is. Well, okay, what's that calculation? Well, here's a simulated calculator. This is the calculator that I use. I'm going to show you how I use this to do these calculations. Obviously, I've done this in Excel as well, but this is the way that I would do this on a test. So I have 3.9 second EE negative 11. That's that KSP value. I divide that by 4, and it gives me 9.75 times 10 minus 12. In order to solve that, I have to take the cube root of both sides. So I will do a second and math. No, that's not what I want to do. Second quit. Second. Oh no, I don't need second. I want math. Cube root. Too far, too far, too far. Cube root. And then I want to take that of the answer that I just got. And that gives me 2.136, blah, 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 blah. All of those decimals out there. Now, how many sig figs should I have? Well, I had 2 in my first number. It's 3.9 times 10 minus 11. So it should be 2 decimal places right here. So 2.1 times 10 to the minus 4th is the number that I should be reporting. And if we go back and look at our slides, you'll see that that's the value that I have here, except I've reported it to the wrong number of sig figs. Go me, awesome. Now, are sig figs important? Yes, of course they are. Do I need to pay attention to them? Yes, I really should. Do I always? No. Are you going to have to on your tests? I'll put it to you this way. The way that I grade my tests, I will choose one question, one out of all of the things that you have to do. And I will look at that to see how you've handled the sig figs. Do I know what question that's going to be when I grade the test? No. Do I know what it's going to be when I grade the test? Not usually. I just kind of pick one and go with that, and everybody gets, graded for sig figs on the same thing. Now, if you do it wrong on other ones, I will probably give you feedback about that, but I'm not going to straight take points for it. Okay. So that's how we get the 2.14 times 10 to the minus 4. Again, wrong number of sig figs, but that's how you get it. That's my Ca2 plus, and that's what they asked me for. But I also have to put in this equilibrium value for F minus. And if I want to do that, I need to look at my calculator again, because I know that that's going to be that answer times 2. Because that's what's in my table. I have a 2x in that table, which you can probably see just behind that. So that 2x is 4.3 times 10 to the minus 4th. Okay. And that's the value that you see in this table right here. So that's how we solve this in the standard case. So if I just have KSP, no other source of anything, that's the solubility that I'm going to see for them. Now we want to know what happens if we have a common ion. So I want to consider the exact same reaction that we just considered, but I have 0.05 molar NaF in the water before I add that CaF2 to it, okay? And then I want to, again, ask that question, what is the solubility of Ca2 plus? So on my piece of paper, I don't have a lot of space here. But I know that it's going to be very similar to what I've already done. So what I can do is copy that. Oh, wait, actually, draw it again. I apologize. So I'm going to copy that. I'm going to put it on the next page. Come on, slide over. I'll put that down, and I'm going to move it somewhere where it's useful to me. And then I'm going to have it be there. Go, awesome. Now, not everything is exactly the same because we don't have that initial condition where everything is 0. So we have a starting condition for our F minus. So this right here is going to change. And that initial value for the F minus is the 0.05 molar. So I'm going to pull that back up and put in the 0.05 molar. Okay. That means that my change is actually going to be that 0.05 plus the 2x. Now I won't include that 0.05 there. For me, the change is only about how the x's affect things. So that means I'm going to have different values down here. So I'm going to go ahead and get rid of those. And what I'm going to find is that my 3.9 times 10 to the minus 11th, my KSP value, is now equal to this x for Ca2 plus times the 0.05 technically plus 2x squared. Now, can I do that way and solve it with the x there? Yes, I can. But I initially am going to make the assumption that the x is very small comparative to the 0.05. So I'm actually going to take this out and leave it as just 0.05 squared. Now, if that's 0.05 squared, then I'm going to take, what is that 0.05? Because I'm not very good with math. Go me, 0.05. We'll square that, which should be 0.0025. So I have 0.0025x, 3.9 times 10 to the minus 11th. I'll divide both sides by the 0.0025. And that's going to leave me with an x equal to whatever that calculation comes out to be. So I have 3.9 second exponent negative 11. And we're going to divide that by 0.0025. And that gives me 1.56 times 10 to the minus 8th. And that's what I would put in here, 1.56 times 10 to the minus 8th. This would then be the 0.05 if I wanted to do the test to see, is it reasonable to assume that the x is small? What I'm looking at is, what is the value of x? So this is my x value, the 1.56 times 10 to the minus 8th, divided by that initial value that I have, the 0.005 times 100, because I want to see what percentage that is. So if I divide this by the 0.05, and then I multiply that by 100, that is nowhere near 5%. So if it's lower than 5%, that is a valid thing for me to do. And and my assumption that x is small comparative to the 0.05 is actually true. So that was a valid assumption for me to make. And yay, I have verified that. So happy. Awesome possum. And that should be what we see in our table, which is what we see on our table. Now, again, this should actually be 1.6 times 10 to the minus 8th. And this is the 5 times 10 to the minus 2 that you have here. Okay. So sig figs, bearing sig figs in mind, this should be a 1.6. All right. And just as I expected, the Ca2 plus is less soluble here than it was here, a lot less soluble. And that's what I would expect. So that's how we take that into account. So we now have a source of F minus that affects how much of that Ca I can get into solution. Effectively, what we're talking about is, if I look at this reaction, So if I look at this reaction right here, the CaF2, CaF2, where's my pointer? CaF2 going to Ca2 plus the 2F minus, because there's already 2F minus there, I'm going to have to slide this backwards, which indicates that I will have a lower solubility for Ca2 plus. So that is Le Chatelier's principle in action. That's what you're looking at. Awesome. Hopefully there are no questions, comments, problems, but if there are, you know the drill. Let me know what we were talking about, what your question is, and I'll be happy to answer it, okay? So let's go ahead and move to our next slide. Now we're going to calculate solubility with a common ion. So this is just another example of the same thing that we just went through. So I'm going to take and pull up my piece of paper here, and I'm actually going to cover up my calculator with this for now and see if we can get this so we can see both at the same time. So this is the slide that I want. So what's the molar solubility of CaF2 in 0.01 molar CaNO3? So now I'm looking at CaF2, again, going to Ca2 plus 2F minus. I don't care about that because it's a solid. This is aqueous. This is aqueous. And I have a 0.01 molar, 0.010 molar. So there's that right there. So that's what my initial is going to look like for this. My change is still going to be the same. I'm going to get a plus X here and a plus 2X there. We will again make the assumption that the X is very small. And so that means that I'm going to set my 3.9 times 10 to the minus 11th equal to my 0.010 times 2x squared. So I'm going to divide both sides by that 0.010. And I'll pull my calculator back up so I can do that. Woohoo! So 3.9 second E negative 11 divided by 0.010. And that gives me 3.9 times 10 to the minus 9th. And that's equal to 4x squared. So we'll divide by 4. And that again gives me that 9.75 times 10 to the minus 10th, different exponent this time, but same value. And now I need to take the square root rather than the cube root. So my x is going to be equal to the square root of that number. So I'll go ahead and do second square root, second answer, and that will be 3.1 times 10 to the minus 5th. Now notice something, at least I noticed something. We have a lower solubility here than we did before, right? Because what we had the previous time when we talked about this solubility here for my for F2 minus was 4.27 times 10 to the minus 4th, right? And we're now looking at 3.1 times 10 to the minus 5th. So that is a difference, okay? One of the other things that I see in doing this is that there's a bigger change in the Ca concentration based on what my fluorine concentration is than there is in the fluorine concentration comparative to what the Ca is. So now that I'm doing the other ion, it's a bigger effect than what I saw previously. And the reason for that is the stoichiometry, okay? So that's one thing that you may be able to look at for that. Now, if you wanted to do the check to see if this is a valid assumption, we take our 3.1 times 10 to the minus 5th divided by the 0.010 times 100. calculator because I'm no good at this. So we'll divide this by the 0.10. 3.122498999. And I'm just trying to get back all the digits that I can see from that thing before I screwed it up. And then divide that by the 0.010. And then multiply that by 100. Again, that's less than 5%. So it's a valid assumption for us to make. And that's the kind of thing that we need to be looking at. All right. Now, do I expect that you're going to test it every single time? That's up to you. I mean, I know for me, I would test it because if it wasn't a valid assumption, then I would want to go back and calculate it appropriately. Are you going to be close? Absolutely, you're going to be close, but it's not going to be the same. And so that's something you want to think about. Are those points that you want to be able to get? Making that wrong decision is not going to be an all or nothing. So if we're talking about a 20-point problem, we might be looking at as much as 4 points for doing it wrong, but it's going to depend on what everything goes into this. So there's a lot of math that goes into that. If that's the one thing that you do wrong, then it's not going to be worth that much. Okay, so that's something you need to be able to think about. Questions, comments, problems on that process? I hope not. So let's keep going. And let's not forget, there's a couple of things that we want to think about. Not only does the presence of a common ion affect the solubility of the salts, but it can also change the properties of the solution. So it is possible that one of these things, like that F minus, could react with water. And F minus does react with water, doesn't it? It does. So F minus plus H2O is going to give me HF plus OH minus. And so that will change the pH properties of the solution. So there are other things that can happen based on the nature of the ions that we're looking at. So if we have the conjugate base of a weak acid or the conjugate acid of a weak base as part of our salts, that's something we're going to have to be concerned about. Okay, so you may get asked about things like that. I may ask you, what's the pH of the solution? I may ask you something about if I were to add acid or base to this, what would happen? You know, I could ask you, is this going to be a buffer solution? Things along those lines. So you have to be able to think about, and the key here is what's in my beaker. That's what it is. Instead of thinking about a single reaction being in that beaker, now we have to think about multiple reactions going on in that beaker. And so we have to think about what could possibly happen. Now, Ca2 plus doesn't react with water. It doesn't. But F minus does. So we have to be able to think about that too. So if the solution is a weak acid and then we add the common ion, we then form a buffer. Okay. So that's something that we have to think about is, are we just going to change the pH like we do here? So we're changing that pH because of the presence of the F minus ion, because that will react to give us the OH minus, which will then raise the pH. Or are we creating a buffer in that case, in which case we have to think about how that's going to behave when we add an acid or a base to it. And of course, if we end up in a buffer situation, we want to be calculating pH using the Henderson-Hasselbalch equation. And remember, when we do that, we need to make sure that we're talking about molarities. We'll talk about the difference, you know, when we do what in a little bit, or at least sometime later. The solution itself will be less acidic than it was because the acid is less soluble, okay? And the solution is able to buffer the addition of base or acid due to the presence of the common ion, okay? So my happy little note, isn't it fun when we consider all the things that can happen instead of focusing on only one equation? So that's where we're getting to, is now that we're learning about all of these different types of equilibria that can happen, you're going to be expected to think about all of those things. So I have a solution that gets made. What are going to be the equilibrium values? And in order to think about those equilibrium values, I have to be able to think about what else might happen. Okay, So we have to think about that too. And we'll talk about how we do that. Now, the common ion effect, whenever a weak electrolyte and a strong electrolyte containing a common ion are together in solution, the weak electrolyte is going to ionize less than it would if it were alone in solution. The hell did I just say? So weak electrolyte, here's the CaF2. That's the weak electrolyte that we're talking about. Strong electrolyte is that F minus ion. So that came from sodium. So NaF, that's where that came from. So that's a strong electrolyte. That's going to dissociate completely